Hi everyone, so let's continue from where we stopped last time. So last time we have seen pooling mean difference and also pooling pre-calculated effect sizes. We have already covered that. That was on part 11. Today's will be part 12. So we will continue from that, and today's session will be about correlation. But if you haven't watched some of the previous tutorials on pooling effect sizes using a meta package, I suggest you can maybe watch them so that things get clearer as we go along through the coming sessions. So for today we will talk about correlation. So if you know correlation value starts from -1, so it could be 0 to 1. So it's always within this range. So it's between -1 and 1. So correlation, I don't have to go through this, but I think you know from your basic statistics class, this is how correlation is calculated, and this is how the standard error of correlation is actually calculated. Just to remind you, there are many different kinds of correlations, Pearson correlation, or maybe this rank-sum correlation, or maybe some other correlation methods like Kendall-Tau or point biserial correlation. And there are many different types of correlation. I mean, you can go through them and you can check actually which one to pull with each other. Do you have to pull like Pearson with Pearson, or you can combine Pearson with some other correlation? It's you have to check you have to check that. But I don't want to talk much very detail about that. So what I said before is like the correlation is always between -1 and 1. So it's kind of, when you look at this distribution, so the value of the correlation is always between -1 and 1. So that means the distribution is skewed. So it's skewed between these values. It doesn't go beyond below this, or it doesn't go above this one. So what you do is you have to transform it. You have to transform it so that you can achieve a normal distribution. So to do that, you have to use the transformation. It's called Fisher-Z transformation method. And the way it's calculated is actually you take the reported correlation, and then you simply add 1, and then at the denominator you subtract it with 1 minus, and then you divide it. Then you take the natural logarithm of it, then you divide it by 2, and that's called Z-core transformation. So with that means you can kind of convert this skewed distribution into some kind of normal distribution. After that, you can use the previous effect size, the previous weighting methods. You can take the inverse variance method, and then you can kind of pull the effect sizes. You can pull them, you can combine them together. But luckily, we are not into that. We will not go through all of that because we have a package. There is already a program written for us, so we don't have to convert anything. We just plug in the untransformed correlation value with sample size. So the software, the MetaCore, I mean the function itself, will do the transformation. So you don't have to do anything. I mean, if you want to do this by hand, you always have to remember that you have to do the transformation, this Z-core transformation, and then after that you have to do the weighting and the pooling process and the pooling procedures. But luckily, the function is already there in the package. We will use a package, and then the package will just do the transformation. So this step you can ignore it if you are using the package. But if you are doing it manually, if you are calculating it the pooling them by manually, then you always have to remember that you have to transform them so that you can achieve the normal distribution. So the package, actually you need MetaCore function, MetaCore, that's what you need, and the MetaCore function requires just 2 arguments, and that's the correlation value, that means the reported R value that is reported from the papers, and then you also need the N, and that's the sample size. That's all you need. You don't need anything else. It does the package, the MetaCore, the function does the transformation, and the pooling is also done automatically, so you don't have to worry about that. So for today we will use the MetaCore function. Let me just minimize this, and then let's get our hands dirty. So the paper that we will, the data that we will use is actually coming from this, and they are correlating. I mean, they are meta-analyzing. It's actually one of the large how many studies? It's like 29 studies, I think. So there were 29 studies. That's fairly large. It's not bad. 29 is a good number of studies. So what they are doing is they are meta-analyzing the reported correlations reported for health status and subjective well-being. So they are checking how they are. So they are taking studies that reported the correlation between these 2 values, and they are meta-analyzing them. So let's check here. So they have 29 studies were included, and the pooled effect size of the association between health status and subjective well-being was medium. So they had a medium correlation value, and that is statistically significant. So it shows positive. The pooled R is positive. That means they are positively correlated, and the value is actually 0.347, and the 95% confidence interval, you can see it. There is the Q statistics is really high, and then you can see the heterogeneity score, and it's also significant. So that means there is significant heterogeneity across the studies. It's showing statistical heterogeneity, but we can see some of the other heterogeneity measures like tau square, but you can also hear the Q statistics is really high, so that means there is high heterogeneity. Let me scroll down to the later section, what kind of software package I have used. We are going to do it with R, so that means we are going to use probably a little bit different pipeline. That means at least the tau square, if they are using Stata, the tau square estimation will be different. Maybe they are using their Simonian, the pretty kind of standard, de facto standard in the Stata or other software package. But if you are using R, luckily we have additional more robust techniques to estimate the tau square, and that's a restricted maximum likelihood estimation technique. We have already covered that in our previous sessions. Yeah, so here they are saying the meta-analysis procedure. Actually, here we want to see the statistics. So they are saying they are using Stata 13.1. So that means it's obviously they are using the Simonian method. That's a default, I think, in the meta command in Stata. And then they are also saying effect sizes are, so this is an interpretation of the value of the correlation. So if it is 0.1, that's small effect size. 0.3 is kind of moderate or medium. But if it is more than that, you can say a large or strong effect. I think that's the rule of thumbs for correlations. And then they are saying to test whether the association between health status and subjective well-being varies across subgroups. We used Cohen's Q, Fisher-Z transformation of R. That's actually what we have said before, and they are saying between groups. And then here they are also saying by convention, if z-score value is greater than or equal to 1.96 or equal to minus 1.96, the two correlation coefficients are significantly different at the minus 0.05 significantly. That's kind of usual statistics that to decide whether something, some value in the confidence interval is actually statistically significant or not. Yeah, so without wasting our time, let's just scroll down to our R. Then what we do, as I said, is meta-analysis of correlations, and then for that we need some package. So one package is meta, because that's the function that we want to access, the meta function. We will use that meta4 function. And then here we need also to load meta4 because we want to access the restricted maximum likelihood. That's the tau square estimation method. And the dmetar is actually to access this data is kind of publicly available, but it's part of this the dmetar package. So we will access that data, and it's actually called health well-being. And we will do some, maybe if we do some data manipulation, we can also use dplyr or something. Just to avoid the base R way of doing things, and it's much easier to use the package. So let me run this and load my package. So the packages are already loaded, and let's have a look how the data looks like with Glimpse. So you have here are the orders. That's actually the one we can use for study level. Then you have the correlation values. We already have the correlation values, and also we have the n values. These are actually most important things to get our pooled correlation. The other ones are like additional variables. This is we can use it for study level, and this one, the population, is actually if we want to do some kind of subgroup analysis, we can use that. And if you know the BCG vaccination systematic review and meta-analysis, they have also this thing called latitude. I think they were like dividing, doing subgroup analysis by the latitude, by that means the location of the country. So the location of the country is actually relevant in some of diseases, for example tuberculosis, because there is obviously high exposure of tuberculosis for TB exposure. So that means antibody which will be produced against TB might be relevant in boosting actually the effect of the vaccine. That's why in some of the cases you may need the latitude or maybe the country variable. We can kind of convert it into also geographical locations, like in terms of subcontinents. Like let's say you have Middle East or Far Asia, Far East, or things like that, or Western Europe, Eastern Europe, those kind of stuff, or North Africa, Southern Africa, Central Africa, Eastern Africa, things like that. You can divide that and you can do subgroup meta-analysis. So here what we do is we are using metacore function. So you use a metacore, and I'm assigning it R as R, and then you give the metacore function requires correlation. That means the first argument is core. That means correlation. So you assign that core. In our data is actually assigned as COR, and then we give it a core. Now we need the sample size of the studies. That's n. Luckily, it's exactly the same, so we can use n. Then finally, you can add additional arguments data. This is actually important argument. Otherwise, you can also do it like with the $sign healthy well-being $COR, as well being $N. Yeah, you can do it that way. What I mean is like this. Let me copy this, and then you can do this like this, and it works. But I don't have to do that because I can simply give it a data argument, and then it works. As I said previously, the fixed defect meta-analysis is actually for theoretical purposes. You may need it, otherwise for writing, for analyzing your data or something. I don't suggest. I don't recommend using fixed meta-analysis by any means, unless you are dealing with the same kind of study repeated multiple times in the same group of population. Otherwise, I don't suggest using the fixed effect meta-analysis. So that's why we are turning it off by assigning fixed to false. But we need a random effect meta-analysis because we want to do the random effect meta-analysis. Random equals true, and then the tau square method, the tau square calculation, the tau square estimation method is assigned as REML. That means restricted maximum likelihood. Then after that, there's the summary function, as always, as you do the normal linear regression or whatever kind of statistical model. You can call the summary function and then pass your R here, I mean the pooled correlation that we have seen. Then I can simply run it. So now I already have the meta-analysis here. So I have the studies, the correlation values, and here I have the 95% confidence interval, and here I also have the weights. So that means the random effects weights. Then at the end, what you have is like we have the number of studies, 29, the number of observations are about really large. This will be almost 1 million. So it's really large because we also have too many studies actually. So it's almost 1 million, and the random effects model is telling us the correlation of 0.3632, and then you have 0.3105 to 0.41, 0.41 actually. That's a confidence interval, and then yeah, it's statistically significant, so that means the correlation is significant. Based on the rule of thumb of the strengths of correlation, you can label this as median correlation, exactly as they have labeled it here. They say it as median, so there is a moderate correlation based on that definition. Yeah, so let me go back and then let's see additional values. So the tau square is 0.024. This is large, and then now that's the tau square, and the tau value is actually 0.15. This is not a small value, this is a large value, so that means there is really high heterogeneity. So that means I square is also 99%, and then the H statistics is 24.14, and then you see the confidence intervals. And again, this is a Cochrane, the Cochrane Q value, and this is defining again heterogeneity. We will come back to discuss some of these points in the next sessions, but still you can see there is really high heterogeneity. And the method is telling you the meta-analysis methods that we have applied. This is a restricted maximum likelihood estimator that we use for tau square, and we also, as always, we use the inverse variance method. And then the Q profile method was used for confidence interval for tau square and tau. Yeah, so these are the values, but I think what I report here is 0.347. It's a little bit different than the one we have. The one we have is about 0.36. It's a little bit. The other one, if you actually approximate it, it will be, if you round it, it will be 0. That's actually what I report. Let me see here. Yeah. So it's the minus 0. This one here, I already wrote it. So this is what I wrote, 0.35. If you round it, 0.35, but here it's 0.36. Maybe let's check if that is because of the method tau, because it's kind of the default, not the default, the de facto standard method in R. If you use like not really. What I mean is like this is actually the default in R. If you use R, this is a default. You may not have to define, but it's exclusively defining explicitly. What I mean, explicitly defining it is actually recommended. So here is method tau, it's REML, but as you remember here in this paper, they use theta. So that means they don't have access to this tau square estimation. Probably they have their synonym. They didn't mention that. It's really recommended to mention that in your meta-analysis. You should not forget that. Maybe let me check if they actually mentioned that. Their synonym. No, they didn't. Actually, their synonym. No, so they didn't mention that. There's only a layered. Actually, the other author is actually layered. So they didn't mention that. So, but if you are writing a meta-analysis, you always have to make sure to mention what is a tau square estimation. Yeah, you need to detail your meta-analysis methods. And so, since we suspect they are using DL because they are using theta, so let me just replace error with DL, hoping that we will reproduce the results. Now let me check. I don't think there is a difference. There is a little bit difference in the confidence interval, I think, but otherwise the random effect model, the pooled effect size is the same. So it's the same as what we had before. Maybe they have additional, I don't know, additional adjustments. I cannot really say it. But let me get back to my de facto standard. That's REML, and then let me run it. Yeah, so you see the previous one had 0.3633, and this one is a little bit smaller than what we have. So their DL, it's a little bit overestimating the pooled correlation estimate. It's a tiny, very tiny difference, but sometimes if you have a small number of studies, this tiny difference may, if you have a small number of studies and then a smaller sample size, this tiny difference may get larger and may also, you never know, it may change the direction of maybe not the direction, or at least a significance level of your estimate. So it may kind of mislead conclusions or maybe public health recommendations or medical decisions if you really use a meta-analysis method that is kind of not as precise as you want it to be. So since so you have to use REML if you are dealing with continuous outcomes. Yes, so the next thing, we already have the model now, we have the meta-analysis, the pooled effects. The next thing is we need to plot it in our in a forest plot. So to do that, you can simply use forest or R or forest meta. That R is the correlation to model that we just assigned here, and then after that we don't have to add many arguments. I mean, the forest meta, it has really plenty of arguments. You can include some of them, but I think for now we can simply basically run this. But if you're running into many different meta-analyses or something, you can do so many adjustments with this forest meta. I mean, you can use many of the arguments within this function, and then you can achieve whatever you want to achieve. Yeah, so this is how our forest plot looks like. So we have our study, we have our total here, total sample size. That's what we need actually. So we have some studies which are really large, about 350,000 people participated, and then here about 485,000. It's really large again. So that means that's why you see confidence interval are really very close. I mean, in this case you have 0.34. Actually, when it's rounded, that means it's between 0.34 and 0.34, but in reality this will go into smaller digits. This might be a bit different. It will not be exactly the same. Otherwise it would be a point estimate and the confidence interval is within the point. I mean, it should be within, but at least there should be some difference. That's why again here also, so the point estimate is somewhere here, but you have to go extend the number of significant digits so that you can see the interval. Otherwise, just because of the sample size, they also have a larger weight, 3.8 here, and then another one is also having again a little bit larger weight than most of the other studies. But I think the random effect meta-analysis does what the random effect meta-analysis is. It plays with the weights. Yeah, that's all we have for correlation. Next time we will talk about other meta-analysis questions. Until then, into meta-analysis.